In this video, I will introduce geometric series. A geometric series is one of this form, sum from n equals 0 to infinity of x to the n, where x is a constant, a real number. So it is not just one series, it's a family of them. For every real number x, I get a different series. In a previous video, and I will add a link in the description, I attempted to calculate the value of this series being very careless, and in doing so, I made mistakes and I got contradictions. Now I'm inviting you to try to do the same thing, but carefully starting from the definition of series. And if you do it carefully from the definition of series, you will see that for some values of x, this series is convergent and it represents a number, and for other values of x, it is divergent and it does not represent a number, and that will get rid of all the contradictions. And then we also want to know, for the values for which it is convergent, what is the value of the sum. When you're ready, continue watching for the answer. I'm fixing a real number x, and I'm looking at this series on infinite sum. And as we know, an infinite sum is defined as a limit of partial sums, sk, where I'm defining sk as the same sum, but stopping when the index is k. Now the advantage of looking at the partial sum is that now this is a finite sum, and I have many more tools to deal with finite sums. I know I can manipulate it, and that's exactly what I'm going to do. Let me expand the terms for this finite sum. Sk equals, when n equals 0 is 1, when n equals 1 I get x, and then I get x squared, all the way to x to the k. And the trick is going to be to multiply this sum times x. And let's see what happens when I do that. 1 times x is x times x is x squared, x cubed, so on, and the last term is x to the k plus 1. And now I compare both lines, and I notice that most of the terms look very similar. In fact, all the terms here, except the first one, are the same as all the terms here, except the last one. The last term before x to the k plus 1 is x to the k. So if I subtract those two lines, those terms will cancel out. And that's exactly what I'm doing to get a nice expression for sk. Sk minus x sk is going to be the first term here, 1. All these terms cancel, minus the last term here, x to the k plus 1. And now from here, I can solve for sk, which is what I wanted, by taking sk common factor and multiplying by 1 minus x. And finally, I get that sk is equal to 1 minus x to the k plus 1 over 1 minus x. This is only true if x is not 1. I cannot divide by 0. Now I don't have to worry about the case x equals 1, because when x equals 1, look at the original series, I get the sum of 1 plus 1 plus 1 infinitely many times. I know that's going to be infinity, that's going to be divergent. So I don't care about that one. And for all other cases, I now have an expression for the kth partial sum. That completes the first step. So now we're ready for the second step, which is taking the limit of this expression. Now the sum from n equals 0 to infinity will be the limit of partial sums, and we have a formula for the partial sums. For the purpose of this limit, the variable is k. X is simply a constant. So this limit, using the limit laws, can be rewritten like this. Assuming this limit exists, of course. And now, this limit actually exists for some values of x, and it doesn't for other values of x. More precisely, the easiest case is when x is a number between 1 and minus 1, not included. When x is a number between 1 and minus 1 not included, this power has limit 0. And so the full series adds up to 1 over 1 minus x, and it is convergent. For example, when x equals 0.5, you take a very large power of it, that approaches 0. But that's only true when x is between 1 and minus 1. What happens otherwise? Well, if x is greater than 1, then this limit will be infinity. For example, when x equals 2. Or in other words, the limit doesn't exist. When x is smaller than minus 1, this limit will also not exist. For example, when x is minus 2 this sequence would be -2, 4, -8, 16, and so on. It oscillates, and it doesn't exist. When x equals -1, I get the sequence -1, 1, -1, 1, -1, 1 also doesn't exist. And finally, we had already removed the case x equals 1. So in all other cases, when x is greater than 1, smaller than -1, or 1 and -1, this series is divergent because the limit doesn't exist. What it means is in those cases, the series does not represent a number. This is the well-known formula for a geometric series, but it's important to remember it only makes sense when x is between 1 and -1. In all other cases, do not treat this as a number because the series is not convergent. And that is the final answer.